Our global energy consumption is tracing a steep exponential curve. We burn through fossil fuels, split atoms, and capture the sun. But eventually, we will hit a hard mathematical limit. Earth has a finite amount of available energy, and we are rapidly approaching the day we exhaust our planet's total output. In 1964, the astrophysicist Nikolai Kardashev proposed a metric to classify advanced civilizations based entirely on the magnitude of their energy usage. By this Kardashev scale, humanity barely registers. We currently sit at roughly type 0.73. This logarithmic scale compares the power limits of planetary and stellar civilizations. A type 1 civilization manages to capture all the energy reaching its home planet, about 10 to the 16th watts. But a type 2 civilization commands the total output of an entire star, reaching 4 times 10 to the 26th watts. That is 10 billion times more power. Crossing that threshold is a matter of strict technological necessity. To survive deep into the future, a growing species must leave its planetary cradle and tap directly into its star. In 1960, the physicist Freeman Dyson formalized a concept for how an advanced society might achieve exactly that. He envisioned a megastructure built to enclose a star and capture its radiant output. Popular culture often visualizes this as a solid, rigid shell, but physics forbids it. A continuous hollow sphere built around the sun would face immense gravitational stress and intense radiation pressure. It would tear itself apart almost immediately. The scientifically viable alternative is the Dyson Swarm. Instead of a solid wall, this model uses millions or billions of independent, ultra-thin solar satellites, all orbiting the star in a massive, coordinated web. The swarm model bypasses the structural limits of gravity and tension. It turns an impossible physics problem into a solvable, strictly logistical engineering puzzle. Building a net to catch the sun's light requires a surface area millions of times larger than Earth. That demands raw materials on a scale our planet simply does not possess. If we tried to harvest the required iron, titanium, and silicon from Earth, we would have to hollow out the mantle and strip the crust. We would destroy the very home we are trying to power. Instead, we have to look outward and treat the rest of the solar system as a quarry. We would need to strip mine the asteroid belt or completely disassemble a metal-rich celestial body. The most logical target is Mercury. Its high metallic density and proximity to the sun make it the perfect candidate for total planetary deconstruction. To secure a Type 2 energy threshold, we have to physically dismantle our cosmic neighborhood. We consume our neighboring planets to build the infrastructure of our future. Human labor cannot execute a project of this magnitude. The disassembly of a planet and the construction of billions of satellites requires autonomous, self-replicating robotic factories capable of exponential replication without human oversight. Once those satellites are launched, managing them requires advanced artificial intelligence. Billions of objects sharing a tight orbit around the sun run the risk of catastrophic chain reaction collisions, a massive Kessler syndrome that could wipe out the entire swarm. After capturing the energy, the swarm must deliver it. The satellites would use highly focused lasers or microwave radiation to beam the harvested power wirelessly back to Earth or to deep space orbital stations. Simply capturing the photons is the easy part. The real challenge lies in maintaining 1 trillion moving components through absolute automation and flawless orbital choreography. When the swarm is fully operational, humanity officially reaches Type 2 status, commanding a continuous flow of 4 times 10 to the 26th watts of power. When such boundless energy allows us to construct and power millions of massive orbital habitats, known as O'Neill cylinders, we could house trillions of people in perfect artificial climates, permanently erasing planetary overpopulation and resource scarcity. We could route the star's output into nested layers of computational megastructures called Matrioshka Brains, effectively turning the entire solar system into a galactic-scale supercomputer. We could even focus the swarm's immense energy into tight beams, pushing massive light sails and driving spacecraft to relativistic speeds for interstellar travel. By capturing the full output of our star, intelligence breaks its dependence on a single world, actively reshaping the structure of its solar system. The link between expansion and energy is so consistent in the progression of technology that astronomers search for these megastructures as a signature of mature life elsewhere in the galaxy. That is why the search for extraterrestrial intelligence actively scans the sky for the specific mid-infrared waste heat that a megastructure would bleed into space. The laws of thermodynamics dictate that processing this much energy creates entropy. The waste heat cannot be hidden. A functioning Dyson swarm emits a thermal signature that acts as a beacon across the galaxy. A Dyson swarm represents the theoretical upper limit of a star-bound civilization's potential. As we scan the deep infrared for these signatures, we are looking for evidence of a future we are only just beginning to imagine.